Well, good afternoon, everybody. This is Gene Bohensky from IR Thermal Systems. Thank you for coming to today's webinar. The title is The Operation and Maintenance of Process Dryers Best Practices. And in this webinar, we're going to attempt to go over some of the things that we've learned over our 30-year history in the business of operating and maintaining large process dryers, whether that be hot air or IR dryers. We're going to go over some basic best practices, and then we're going to have our expert, Jason Allington, go over a specific example that he worked on with one of our customers. So let's first start with an introduction to our company. We were founded in 2020 after the former management team purchased the assets and intellectual property of Radiant Energy Systems and Anderson Thermal Devices. Our management team and employee have experience since 1985, so we have a long history in the business. Our core competence is the design and manufacture of custom engineered process heating solutions for improving performance and lowering production costs. We focus on quality and dependability. We constantly invest in the latest manufacturing technology, and we produce our own high-quality component parts. For example, the stamp foil heating elements you see it right there. We're focused on continuous heating processes, and we're also technology independent, and that allows us the freedom to choose the best technology for the customer's application. That means we both do hot air and infrared heaters and dryers. So what we focus on mostly are preheating, drying, and curing applications with hot air systems and combination hot air systems and infrared. Our systems increase line speeds, reduce energy costs, save space. We level out uneven temperature or moisture across the web. We can heat selected zones across the web, and we also provide infrared retrofits that can help existing systems maximize performance. So industries we serve include converting, paper, film and foil, printing, nonwovens, plastic, adhesive lamination, batteries, medical devices, filter media, fiberglass, advanced composites, industrial fabrics, automotive, packaging, wire and cable, textiles, and many others. So our range of drying methods that we provide include convection hot air systems, including impingement drying systems, flotation drying systems, through air drying systems, batch dryers and ovens. For radiant heating and infrared drying systems, we have both electric infrared and gas-fired infrared, and we also have combination infrared and hot air systems, where we typically use IR as a booster to increase line speeds and/or improve product quality. So each technology has their advantages and disadvantages. Since we are technology independent, we are free to choose which is best for your application. So as an introduction to this specific presentation, we found that effective dryer operation and maintenance ensures longevity, safety, and cost effectiveness, especially given potential deviations from design specs which may occur over time due to business considerations. So this presentation aims to guide the comparison of initial operating specs with current performance. We offer maintenance strategies to enhance efficiency and reduce downtime. Often running new products with existing equipment may lead to new operating conditions, which could affect maintenance cycles of existing components. And that's really important to consider because a lot of times what you're making changes over time. A lot of your dryers tend to be there for a long time because they are large capital expenses. But your products might change over time, and especially as new materials and new ideas come in, you might be making adjustments with your existing equipment. So it's important to review your key operating specifications and particularly the design specifications. Understanding the throughput rate, temperature range, energy consumption, and design parameters that were originally defined with the equipment. These serve as the baseline for evaluating your current performance. You want to make sure you document the original design specs, and this is critical for benchmarking, maintenance planning, and troubleshooting. You can reference the DOE sourcebook for standard metrics, noting that energy use impacts production costs. So energy use is 2 to 15% of your production costs with large-scale dryers and heaters. So for maintenance tips, first is to make sure you do regular inspections. You want to check for wear on any components that do wear out, especially rotating parts. You want to look for damage, leaks. Make sure you have proper functioning of your major components, including your gas train, retraction system. You want to look for fan vibration. You want to do this minimum yearly. And keep a maintenance log that includes your process parameters. You also want to do regular cleaning your heat exchangers, burners, filters, and blowers regularly to remove any scale and debris. And make sure if you do have any filters that you do swap them out on a regular basis. Also, from a calibration standpoint, you want to make sure your temperature controls are calibrated, your infrared thermometers are calibrated, thermocouples, pressure transmitters, and you want to ensure that you have clean instrument air. This is always critical. And make sure you have right FRLs or filter regulators to make sure that they're also in place. On the lubrication side, you want to lubricate any moving parts like fans and pumps. A common practice from HVAC maintenance tips is also if you have any conveyor systems, that those are all lubricated and looked at on a regular basis. And spare parts, make sure you have spare parts, including any spare nozzles to ensure quick replacements during maintenance. So comparison with additional design specs, you want to identify any deviations. Consider common reasons for deviations, such as changing product specifications or operational challenges and their impacts. That can also reduce efficiency or increase energy costs. Use performance monitoring such as temperature, pressure, and flow rate sensors to track deviations. And review your maintenance logs and historical data to identify trends. You also might want to consider conducting an energy audit to compare current energy consumption with the initial design, using tools like the DOE's Measure tool for process heating systems. So for optimizing your dryer performance, you might want to consider this as a project. Optimization ensures your system meets current needs while preparing for future challenges, enhancing your competitiveness and lowering operation and energy costs. Consider consulting work to review and to enhance your dryer process. This could involve reviews to improve efficiency, such as switching materials. In one case study that we were involved with, one customer switched from volatile solvents to water-based materials, reducing energy consumption by 15% while improving safety. Also consider technological upgrades. Explore adding infrared heating to existing hot air processes for better energy efficiency and faster drying. Another case study that we've had, a customer added infrared heating, reducing drying times by 25%. So at this point, I'm going to turn over the presentation to our expert, Jason Allington, who's going to cover the components of dryers and talk about some tips there. So go ahead, Jason.
Yeah, thanks, Gene. The big thing about developing a maintenance plan is scheduling your downtime. There will be downtime on every single system. In order to keep it to a minimum, you want to schedule when it's going to be because the worst case scenario is it happens 1 in the morning when you have a component break. There comes your downtime. So in looking at this example, we had a 4-zone drying system where they had 2 different drying profiles within that drying system. The first zone on the left had a counterflow nozzle over a flotation airfoil, while zones 2 through 4 had flotation nozzles. The upper picture is the top view of the system. You can see the recirculation air plenums located adjacent to each zone, as well as it's kind of hard to see because a lot of this stuff can get complicated. Is the makeup air and exhaust air are ducted in over top of each other in between those systems. It's also important to note that in a system like this, they had their recirculation air plenums located on an upper floor where it was a little more difficult to get access to. So the major components within any drying system are the recirculation air plenum, the dryer body, and the exhaust. Those are absolutely needed. What also is, and everybody is typically, I mean, what everybody can typically see. The parts that people kind of overlook is what each one of those do and where the airflow within them is occurring. So you might have a plenum, but people where you know your return air is coming back to and your supply air is coming from, but also typically that's where your makeup air comes into the system. Also, combustion air comes into that system, whereas your return air ductwork is also often used to pull your exhaust air. That exhaust air can also be taken from the dryer body. Uh, the important thing about understanding where the air coming in and out of this system, it will be seen on the next slide, where I kind of uh, go over the math behind this entire system. Now, this is important to understand how the air flows and the air is balanced within a system because the upsets that occur when something isn't working right can be often difficult to troubleshoot. So understanding the effects of changing exhaust air or makeup air has on a system is important when you understand that the supply air equals the return air minus the exhaust air plus the web slot times two plus the makeup air and the combustion blower. Yeah, understanding how all these work together can be an early warning sign that the system has been upset. If I have a web break and a big slug of paper is caught in my return air ducts, that might not show up except for the fact that I have a flutter problem on the web slot that's right next to that return air duct. If because I'm not getting the return air out of the dryer, so what ends up happening is the web slot might turn positive and you're blasting air out of that web slot. If that's the case, it's important to understand that this understanding how this air equation works also is important because it helps you understand when a system goes to an extreme, if you want to run 100% exhaust or close to 100% recirc. Looking at the individual components, the plenum is probably one of the most important because it has the highest level of sophistication for the componentry that's involved in there with the gas train and the burner control system. That's if it is a natural gas system. It can also be steam or hot oil or indirect natural gas fired, but it's still where the most componentry is located. You'll have the supply fan, which might have a high temp limit switch to make sure that the fan's running on safe conditions. Also, pressure transmitters to understand what my supply pressure is at. The supply ductwork, is often just looked as a method of conveying air to the dryer, but it also serves a couple other purposes. It provides an area for the proper mixing of the heated air. Also, it distributes the air to the top and bottom of the dryer enclosure. It's hard to see, but there are small dampers prior to the supply to the top as well as the bottom. That helps you balance that air top to bottom. Also, every supply fan needs a specific amount of distance to build up the pressure required for delivering that air. So you typically have 2.5 times the diameter of the supply fan in distance within that ductwork prior to having any turns or splits. The dryer itself, you're not only doing the drying, but the dryers are designed to give you once again, the proper distribution top to bottom, But by building air pressure within the nozzles, I also get the proper distribution in the cross machine and machine direction. The dryer itself is also a great location to have particulate gathering prior to the return air, as well as a place to pull off exhaust air. The return ductwork, once again, if I'm trying to supply air as even as possible, it's important to remove that air as even as possible. So as to not causing in order to not cause web shifts or web disturbances. So I typically will have dampers for balancing the top to bottom air. It's a great location for air testing for cleanliness or particulate, and as well as removing messes from web breaks. The exhaust system not only is a way to pull out air during the purge air during startup and shutdown, but it's overlooked because it removes your evaporates as well as your dirt and particulate. That often might have to have a dust collecting system or some sort of volatile sensing system on it to make sure that your exhaust air is being handled in a safe way. It also provides the negative pull to maintain box negative as well as exhausting box negative per zone as well as box negative as the dryer overall. One of the things that happens on every single job, and it's unique for every single job since all of our systems are custom, is developing a critical spare parts list. The foundation for this is the complete spare parts list, we'll put together and say and give an example like this which will be many pages, but we'll give an example like this and then review with our customers the what each component their lead time might be versus price versus the resultant downtime of missing a component like that. Yeah, it's typically a group of conversations together to help work with each individual customer to identify that, hey, part A is a critical spare part. It costs $10 and it takes 6 weeks to get in. So that, if it's gone and since it's critical, we need to have this on the spare parts shelf. Whereas like an LFL monitor, they're crazy expensive and they just don't fail. So this is a part where I work with my customers' maintenance or engineering department to help identify what the most important critical spare parts are for that individual customer. And when it comes to dryer maintenance, overall, this is like the best document I can say that people need to have on hand, and is referred to as a P&ID or process and instrumentation diagram. It is basically a roadmap of the flow in and out of your system, as well as what sensors are located where. It's important often for customers to use this document between engineering and maintenance to identify critical areas. I've even seen where people have taken our document and put together handbooks where they have each component, like a pressure transmitter in zone 1 might be Z1PT 105, and then 205, 305. That would carry through. This way, when engineering is working with maintenance, they can say, go to PT 305. Then the maintenance group can pull up this diagram and they can say, oh, I'm going to go to second floor, plenum 3, on the gear side, and they'll know exactly where that location is. And also, if they have it in conjunction with pictures to identify those parts, it can make maintenance a whole lot easier and avoid extended downtimes due to confusion. This is a simplistic idea, but I don't think people study it enough. It's it's how the control variables versus the feedback work. If a lot of people, don't understand that when I have, I'm controlling the supply temperature, that the the device that's actually controlling that supply temperature is a butterfly valve on my burner. So that whether that opens and closes controls the rate of burn of natural gas within my system. Now, what is telling that butterfly valve to open and close is actually the supply temperature thermocouple, which might be located, you know, several feet or yards, or in the last case I worked on, maybe 200 to 300 feet downstream of it. So it's important to know that, hey, if I'm having a problem with my supply temperature, that I'm not meeting temperature, it not only could be the amount of airflow that's coming into the system, but it could also be a bad thermocouple, or I'm not getting the proper control of my control valve. It's the same thing for the supply pressure, the exhaust volume per zone, and the exhaust volume total. If you're not understanding how that system works, what the control variable is versus the output and the feedback, then troubleshooting that system can be difficult. One of the areas that you see most overlooked on older systems is the natural gas train. Uh, that is what controls the safe delivery of natural gas to an individual burner. And NFPA 86 is a fantastic document that gives you the regulations and recommendations for natural gas system, or for furnaces and ovens. So if people have a furnace or an oven, having an up-to-date copy of an NFPA 86 manual is really important. Or you should be in contact with a maintenance group that does spend the time to keep up to date with those regulations. Because there are specific regulations with gas trains that should be checked every year, that to make sure that the double block and bleed valves aren't leaking over time, that you're not going to slowly flood your dryer with natural gas over a weekend, or you're not going to or ensure that your purge time isn't getting changed over time due to a replacement of the purge timers or adjustments made, during off hours. I don't have a good example of this, so I made something like this up, but this is what a document such as this is I feel a must. And this goes back to where I said that if you don't schedule your downtime, it will get scheduled for you. So coming up with a a task list that a maintenance personnel or engineering personnel can work and sign off on, the sign, date, and initial that the task was completed for each critical component. Now, how you build up when what type of attention each critical component gets is dependent upon the manufacturer documents that we provide during a system. Once again, all of our systems are custom, so we might use one manufacturer versus another depending on the system. So we try to work, with somebody's engineering group or manufacturing or maintenance group in order to help create a document such this at the end of the engineering process.